Hello class, welcome to SciChem. Here we are another session for the lecture number 6 of chemical kinetics. Before watching the lecture 6, make sure that you have already watched previous lecture, that is 1 to 5. So let's go. Today we are going to deal with problem. Here is the problem. So that for a first order reaction, time required to complete 99.9% of the reaction is 10 E. In order to solve this problem, we have a formula of first order kinetics is equal to T. T is the time period, K0 is the initial concentration, At is the concentration left after time T. So we can put here K is equal to y equal to 1 by T. By T means T where T is the time period. What time period? Given time period is T 99.9%. So I can use on initial concentration consider 100 and final concentration left, that is 100 minus 99.9% is 100 minus 0.693 by T half will be equal to by T on spread by 1. And so 0.1 so I can 0.0 equal to by T on 10 to the power 3, and this ln 10 to the power 3 I can solve here 1 by 399 3 ln 10. By converting ln into log, I can get 1 by 399.9% 3 to 2.303 10, and it will be equal to 6.909 divided by 390, and it will be equal to 0.693 by T half. So by comparing both sides, I can have T half is equal to sorry T 99.9% equal to 10 times of T half of T half. Similarly, Similarly, we can solve that T 75% is equal to 2 times of T half, T 87.5% is equal to 3 times T half, T 93% is equal to 4 times of T half. Do it yourself. So next part is, come to next part, second order kinetics. Here the rate of reaction depends upon second power of concentration, that is called second order kinetics. So here we have two cases. Here case, let us consider reaction A gives rise to product. When time t is equal to 0, it have initial concentration. Time t is equal to t, a naught minus x is 80 is at is equal to a naught minus x and bt is equal to x. So since the reaction is a second order, so I can write here r is equal to k into a power 2, or rate is equal to minus dA by dt, minus dA by dt, or dx by, so change in concentration I can write dx by dt is equal to k into a naught minus whole square, or dx is equal to dx by naught minus the whole square equal to, then integrating both sides by taking limits. So I can write here integration of dx by naught minus square, it will be equal to dt. Integration it here 0 to t limit, here I can put 0 to. Similarly here, by solving integration for dx minus by a naught minus x rho whole square, similarly dx by is like dx by, that means x to the power 2 goes above, that is x to the power minus 2, integration for x to the power minus 2 dx, x to the power minus 2 plus 1 divided by minus 2 plus 1. So I can write here dx by a naught minus x whole square, I can write here 1 by a naught minus x to x. How? A naught minus x to the power minus 2 dx integration naught minus x to the power minus 1 into d of a naught minus d of d of. So by solving this I can write 1 by a naught minus x d of 1 into, so a naught minus x, it is also divided by a naught minus x to the power minus 2 plus 1 divided by minus 2 plus 1. Here minus x, it is minus, so minus minus plus, so simply I am writing here 1 by a naught minus 2 equal to at. By solving this, 1 by a naught minus x by 1 by a naught is at will be equal to naught in a naught minus x divided by a naught T. K is equal to 1 by T x into plus x. So this is the derivation for second order kinetics, and that is case 1 when A gives rise to product, and rate here, rate is equal to K into A power, and for this case I have K is equal to 1 by T into x by A naught into A naught minus. Now come to lifetime of second order reaction. It is TLT. Here consider at T is equal to TLT. TLT means time required to complete 100% of the reaction. TLT x is equal to A naught. If we put x is equal to A naught in this equation, I can K is equal to 1 by T into y naught minus, that is K TLT. TLT tends to infinite. So theoretically this reaction also never get completed. This reaction also never get completed. So theoretical lifetime of second order reaction is infinite. Next come to half-life of second order reaction. The half. So at T is equal to T half, I have x is equal to A naught by 2. So by putting x is equal to A naught by 2 in this equation, T half is equal to by K A naught by 2 divided by A naught into naught minus 2. By solving, I can get T half is equal to, the peculiarity about half-life period is T half is equal to 1 by A naught K. This is for second order. This is for second order. For first order, T half is equal to 0.693 by K, and for zero order, T half is equal to A naught by 2K. By comparing second order, first order and zero order, in general I can write T half directly proportional to A naught power plus T half directly proportional to A naught power 1 minus n. So this is all about half-life of second order reaction and lifetime of second order reaction, that is up to case 1. Similarly, we have another case 2. Case 2. For case 2, we have a reaction A plus B gives rise to product, and for this reaction R is equal to K into 0 power 1 0 power. For this case 2, we have further subcase that is case 2a. First we are gonna solve case 2a. For case 2a, consider concentration of both A and B are same, or that is initial concentration of A and B are same. So again I am writing the above equation, A plus B gives rise to P. So when time t is equal to 0, I have initial concentration A naught. Since the initial concentration of both A and B are same, we have initial concentration also. When time t is equal to t, A naught minus x, this is also naught minus x. Why xx? Since it is the reaction which have 1:1 stoichiometry coefficient. So for this reaction, I have R is equal to minus dA by dt minus dB by dt x by I can write here dx by dt equal to A into A naught minus x because R is equal to K into A B. Because R is equal to K into A into B, so A have change in concentration A naught minus x, B have change in concentration A naught minus x. So dx by dt is equal to K into A naught minus or dx by A naught minus K. And this is the same type of derivation that we have already done case of case 1. Dx by A naught minus 2. So this is subcase that is 2a, where the concentration of both A and B are same. But in case of case 2b, consider the concentration of A and B are different. That is initial concentration of A and B are different. So again I am writing the equation as A plus B gives rise to product. So when time t is equal to 0, A have initial concentration A naught and B have initial concentration B naught, since A and B have different concentration. So when t is equal to t, I can write here A naught minus A, it is B naught minus. So here I can write R is equal to minus dA by dt equal to dV by dt is equal to dx by. So overally I can write here dx by dt is equal to k into A naught minus x. Why I am writing this? Since R is equal to k into A raw power 1 and B in k into A raw power n, product of, and B in B raw power 1. So dx by dt is equal to k into A naught minus x into B naught minus. dx by a naught minus a dt. And for solving, integrating both side by taking, so right here dx by naught minus d to d. How integration of dx by a naught minus x into b naught minus x? You have already studied this type of integration, and we can solve this type of integration by partial fraction. Integration by partial fraction. So I can put here 1 by b minus a, so 1 by minus x will equal to 1 by b minus a minus ln a x, integration of dx by a minus x, integration of dx by a minus x, that is ln minus ln a minus x plus ln b minus. By solving 1 by b minus a minus ln a minus x ln a plus, by using the limit ln b minus ln b, and it will be equal to k dt. A is equal to 1 by t and 1 by b minus a ln, by solving this, ln a plus ln b minus x. I am separating the variables such as positive positive same side and negative negative. Ln a plus ln b minus x, so I can write here ln a into minus x divided by a into b minus x divided by minus ln a minus x minus ln b, so I can write here b into plus. So again I am writing is equal to by t into 1 by b minus a ln a into by b into here x is less than a. So this is the derivation for second order kinetics, that is of case 2a, where the initial concentration of a and b are different. But here another question arises. Here a question arises. What is the question? What happens when b is very greater than a? When b is very greater than a, when b is very greater than a, I can say that I can neglect anything with respect to a, with respect to, sorry, not a, with respect to b. Since b is very greater than a, so I can neglect anything with respect to b. So I can write here B minus A tends to B, age x is less than A comma B, so I can write B minus x approximately equals to, so by using this value in this equation, I have k is equal to 1 by t, 1 by b minus a, I can write 1 by b ln a into b minus x, b minus x tends to b, so ln ab divided by a minus x, b into a minus, b gets cancelled, b concentration of b take to that side, I can write b into k equal to 1 by t ln a by minus x, and b into k is another, where b is very greater than, take b is a constant is constant, that is another constant, k dash is equal to 1 by t ln a by a minus x, where k dash is equal to b into k, and this k dash have value 1 by t into ln a by a naught x, it is similar to first order and similar to first order reaction, like so. And this type of reaction, called pseudo first order reaction. The reaction appear to be second order but have rate constant appears to be first order, and this type of reaction is called pseudo first order. And this type of reaction occurs when the concentration of any particular reaction is greater than other reactant. Since here concentration of B is very greater than, since B is very greater than A, so particularly the concentration B of B is constant. So this type of reactions are called pseudo first order reaction. This reaction appear to be first order reaction and it is known as pseudo first order reaction. Here remember one thing, what is the difference between K and K dash? K is the rate constant for second order reaction, this rate constant for second order reaction, but K dash is the rate constant for first order. So what is pseudo order reaction? Reaction in which kinetics of the reactions are studied by decreased order are known as pseudo order reactions, and it happens when any particular reactant is in excess or rate law expression involves a catalyst. So let's consider examples. Example number 1, acidic R is equal to S 3 first E. CH3CO2H5 plus H2O, presence of catalyst H plus gives rise to CH3COH plus, and it have been found that rate is equal to K into CH3COC2H5 power H plus power. Since H plus concentration is constant, so here I can write rate is equal to K dash CH3O4. This type of reactions are called pseudo first order reaction. Since water have large concentration as well as H plus ion concentration have also large, so this type of reactions are pseudo first order reaction, which we can solve by taking a case when concentration of B is very greater than A. So second order reaction involves three types of cases, that is case 1 when A gives rise to product, and for this we have calculated rate constant K is equal to 1 by T into x by A naught into A naught minus x. And another we have case 2. In case 2 we have divided case 2 into two sub cases, that is case 2A and case 2B. Here concentration of both A and B are same, but here concentration of A and B are different. If A and B are different, we have a rate constant this, and this can we solve by for pseudo first order reactions. What happens when B is very greater than A? So these are all the basic regarding second order reaction. Thank you.